Today we're going to talk a little bit more about the type of force that's required to keep an object in circular motion. So I want to start this video off with just a really short demonstration. I have a bucket, and my bucket contains water. You can see that I'm dripping water off of my hand here. And so what I'm going to do is I'm going to swing this bucket over my head. And you're probably sitting there going, Mrs. Thompson, that does not sound like a really wise idea. You appear to be inside. Well, we're about to have a thunderstorm outside, and so I really don't want to film outside, so I think we'll just do it inside, and I trust that the principles of physics will continue to hold true and everything will work out well, okay? So let me back up here a little bit so that you can see everything. We will take the bucket, and I'm going to swing it over my head on the count of 3. Ready? 1, 2, 3. And I am perfectly dry. Okay, once again, the physics principles hold up, and we are able to see that centripetal force, which is the type of force that we are using in order to keep an object in circular motion, actually works very well. Now, why did that work? Let me refer you back to the experiment that you did not too long ago, where you had a pie plate and you had a little section cut out of it, and you took a marble and you swirled it around the pie plate. Now, when it came out of the pie plate, what happened? Well, if you recall, the marble went straight ahead. It did not keep going in circular motion, right? And so what that tells us is that if I have an object in circular motion, and so for this particular, here's my circle right here. The object is moving in the direction of the arrow. And so what you've already learned is that as the object, if I would stop the circular motion right here, the object is going to go off this way. That's where the velocity is going to happen, right? Okay. If I would happen to suddenly, if I'm swinging something around my head with a string or something, and so if I would cut the string right here, the object is going to fly off that direction. If I get it around here, at this point, in this particular moment in time, the object is traveling this direction. And so the object would go that way. And so as you can see, the direction of the velocity is always changing. Now, what happened with the bucket? Well, when I take the bucket and I swing it over my head, the water has a constant velocity in whatever direction it's currently moving. And so when the bucket gets straight above my head, the water, and I'm sure you were thinking that water is going to come straight out and dump all over me, but what happened was at that moment in time, the water was moving this direction. And so it didn't come down. Now, if I would have held it there very long, gravity would have brought it down. But if I bring it up and the water's moving this direction, then I'm going to continue moving the bucket, and when it gets over here, the water's now moving this direction. By the time it gets over here, the water's moving straight down. And so as I swing the bucket is constantly exerting a force on the water to change the direction of the water. We talked about the word inertia as well, and the word inertia just tells me that an object is going to keep moving in the same direction unless I apply a force to it. Okay? Now, because this velocity is constantly changing direction, what that tells me is that there must be an acceleration. And if there is acceleration, there also has to be a force, okay? Because you can't have an acceleration without a force. So what type of force is acting here so that this object is going to keep changing direction and being accelerated? Well, if you think about the bucket, which direction was the only force acting on the bucket? Well, I wasn't pushing up on the bucket. I was hanging onto the bucket and swinging it around. And so the force that I'm exerting on the bucket is when I'm actually pulling inward this direction. Okay, think about if I got a string attached to like a toy airplane and I'm swinging it around my head. So let's say that I've got a toy airplane out here and it's going this direction, and here's the string. And you're looking downward from this picture. So if I'm standing down here and you're standing up above me, here's the string attached to the toy airplane and you're swinging it around your head. Well, where's the force on the airplane? Well, it's right here. This is the only force that's being exerted on the plane. And so therefore, this force by the string is going inward. Okay, so the force is always going inward, and that's called a centripetal force. Okay, very key point to understand. Centripetal force is a force that acts toward the center of the circle on an object that's going around in circular motion. Now, on the document that I gave you that has some sample problems on it, we don't have any sample problems for today, but I did list for you the 3 principles of centripetal force. So the first principle is that circular motion requires a centripetal force. So again, as I mentioned before, if the velocity, remember that velocity has 2 components, magnitude and direction. So even if the magnitude stays the same, the direction of this velocity is constantly changing. If there is a change in velocity, there must be a change in acceleration. If there is an acceleration, then there must be a force acting on it to cause that acceleration. So circular motion requires a centripetal force. Now, in the lab that you just did, in steps 5 through 9, you hung a various number of washers off of the string that you were pulling or you were rotating around your head. And hopefully what you found is that the more washers you added, the less time it took to go around when you had more weight on the string. Well, more weight on the string corresponds to more force. And so what that does, so steps 5 through 9 of your lab illustrates the second principle of centripetal force. And that principle states that the larger the centripetal force, the faster an object travels in a circle of a given size. So if you recall, you had your black mark on your string so that you knew where that was supposed to be. So you knew you had the circle was the same size as you were twirling those washers around. And so the bigger the force you had, the more washers you had, the faster the object went around, as long as you didn't change the size of the circle. So that particular part of the lab illustrated the second piece of the principles for centripetal force. Now, the third piece of the third principle for centripetal force is that at a given speed, the larger the force, the smaller the circle. So in the third part of the lab, you were trying, so this was in steps 10 and 11 down here. In that lab, you were trying to keep the period the same. So you were trying to keep the time that it took for it to go around the same, even though you had more weight on the end. And so when you did that, what you should have found was that the radius of your circle got a lot smaller. And so therefore, the more force you had, the smaller the circle became. So the third part of the lab illustrated this third portion of the principles of centripetal force, okay? So hopefully with these principles and knowing what was being illustrated at each part, you'll now be able to finish writing up your lab, and then you'll be able to turn that in.